Hello, everyone. My name is Daniel Appel, and I am a first-year master's student at Cal Poly Pomona. And today I'm going to be talking about enhancing mobile security using elliptical curve cryptography. So to start off, we're going to take a look at the introduction. And the purpose of my presentation today is to look at the different forms of elliptical curve cryptography, including its regular form, hyperelliptical curves, and supersingular elliptical curves, and how those enhance mobile security. Now, my hypothesis is that because ECC provides a way to have equal security while also keeping the key size down compared to other alternative methods like RSA, that going forward, it will be the best alternative for us to combat quantum attacks and other kinds of security attacks that mobile devices might find themselves at risk of. So going over the objectives, what I want to do is cover the different mathematical foundations of ECC and how those properties can be used in the context of mobile security. And we'll take a look at the discrete logarithmic problem, how each of the forms approach dealing with that, and why it makes it so strong. And now, if we take a look at figure 1 here, we'll see these are the 4 different types of elliptical curves. The main one that we use is the Weierstrass form. This is y squared equals x cubed plus ax plus b. And this form is the most commonly used because it's the most efficient as well as one of the simplest ways. But what's really nice about the alternative forms are that they provide particularly strong methods to dealing with other kinds of attacks that the main form might not be as good against, making it a more secure method overall. And if we look at figure 2, on the left, you can see a 3D scale model of the elliptical curve. And while normally we only look at a planar view, where we get that planar view from determines the type of curve as well as the strength of that curve in protecting against cybersecurity attacks. And so looking at some of the methods that I used, we first have to consider how ECC uses public and private key principles. So it generates these keys based on elliptical curves. That means that the public key is its initial starting point, and the private key will end up being the scalar that we find using point addition, and I'll get more into that later. And what ends up happening is that this creates a very computationally difficult problem for computers to break with current technology. The discrete logarithmic problem, its strength comes from the fact that the multiplier is put over a finite field where that field limit is a prime number. And what that ends up looking like is like a 3D donut kind of model where the graph will actually loop around instead of just going in a linear direction. So that means even if they were to find the value that matches our k value, they won't know if it's a multiple or not. And the other thing is the discriminant, which helps us determine our starting points and is really effective for making these planes that we choose to be more secure. And this is a really strange number, but it's found through a lot of mathematical studying and techniques that they use to find it. And the Weierstrass form, talked about that earlier. A and B are the constants at the properties of the graph, and then x and y is your initial point. Hyper-ECC, on the other hand, is when the genus of a curve actually has a greater complexity. And this means that the key sizes are even smaller and that the computation ends up being faster. And if we look at figure 3 at the bottom, we'll see this is what it kind of looks like. For each hole, we consider that a genus of 1, 2, and 3 in this case. And then supersingular curves utilize isogenies between the elliptical curves, which quantum algorithms aren't able to efficiently solve. At least that's the proposal. Now, taking a look at the point addition, how we calculate that k value is we take p, our initial point, and pick an arbitrary point q. When we draw a line through that, you'll find that it intersects your elliptical curve graph at one other point. And this is always true because it's a mathematical property of elliptical curves. Now, we reflect that point and get our new r value. And we do this continuously. R becomes the new Q value. Do it again with your starting point. And however many times you do that, usually a very large number, is your K value. And that gives us our private key. And so you might be able to see that having the private key lets us go backwards quite easily. thanks to point doubling. But if you don't have the private key, you're going to be doing this for a very long time, an exponential amount of times. So some of the results that I was able to find include that ECC's smaller key sizes reduce computational load, which is extremely important for mobile devices, and their limited power. It's also really effective for digital signatures with cryptocurrency or crypto wallets like Bitcoin or Ethereum, as well as the one-way encryption of mobile messages. Hyper ECC, on the other hand, is an even stronger alternative to regular ECC. It's basically just better ECC, and we'll see a little bit more on that later. And supersingular elliptical curves were actually found just recently to be insecure. There was a recent key recovery attack that was published, and it found that it was able to solve the proposed algorithm in under an hour, which means it's very insecure. So it essentially shut down the future of using isogeny-based elliptical curves for any kind of future quantum algorithms. And finally, looking at some of the conclusions, we can see that ECC offers a substantial benefit over traditional encryption methods like RSA, and we'll see that in Figure 6. In Figure 6 here, I have a comparison between RSA and ECC key sizes, and we'll see that right now, we're looking at about a 1:9 ratio, meaning that ECC is performing at a 9 times better rate than RSA is, and it's just crazy to think that. And this is why a lot of phones are already using it, but not all phones are. And now, while computers might be able to get away with it, as we keep on increasing it, just next decade, it'll become 12 times as bad and then 20 times as bad. And it's really just not going to be able to stand the test of time. And it will reach the threshold where computers can break it far too easily. And then as far as future developments are concerned for quantum resistant attacks, it's very unlikely that it's going to be able to stay secure with that. And lastly, we can see here how the genus 2 curve, genus 3 curve in Figure 7, these are the hyper ECC curves. And what's really important about this is that these curves are almost 2 times or 3 times as good as the original elliptical curves, meaning that in the future, these are definitely what we want to go with going forward in terms of pushing down the line when we have to replace our normal cryptographic techniques with something that's quantum resistant. And these are my references. Thank you for listening, and I hope to see you at the fair.